Okay, let's look at the section 6.1. This section talks about principle of mathematical induction, right? So let's look at that, right? So what we want to prove is for all natural number n, statement P of n is true, right? So the difficulty is there are infinitely many n, so there are infinitely many statements. So it's impossible to prove each one separately. So we have to have a way of kind of proving all these infinitely many statements in kind of a one shot. All right. So let's do that. All right. First, we need to do is we have to show that P of 1. So very first one, right? This guy is true. Right? And the next thing is that if we know that for all k, which is natural number, if we know that P of k, so it's a kth statement, is true, then this implies that P of k plus 1 is also true. Then this is sufficient to show that, so therefore, for all natural number n, these statement P of n is true, right? So this is called the mathematical induction, and the analogy is kind of like a domino effect. Think of a bunch of dominoes, sitting here in line. Then, so number one is basically make sure that we can knock down the first domino, right? So that's called the base step. All right. Then the second step is really make sure that two consecutive dominoes are close enough so that if one gets knocked down, it's going to push the next one. So making sure that the distance is such that if one goes down, the next one is guaranteed to go down. All right. So that's basically what the setup is. But if you know that the first one it goes down, then we make sure that if the first one goes down, the second goes down. If the second one goes down, then the third one goes down. And if the third one goes down, and the fourth one goes down. And you can see that this will keep on going forever. So which means that once one goes down and everything else goes down, right? That's kind of the argument here, right? Let's look at an example here. This is a typical example. Statement is for all natural number n, summation I goes from 1 to n of I, which is basically 1 plus 2 plus 3 plus 4 plus up to n. It's going to add up to n times quantity n plus 1 all over 2, right? We've seen this formula before, right? Let's prove that. So we want to write a proof. So this is proof by mathematical induction. I'm going to just say induction. Right, got that. Right, first step. Right, we're going to do a base case, right, when n equals 1. So this is called the base case or base step. Maybe I'll call it base step. Right, so this is when n equals 1, right? Right, so we have to make sure that this formula is valid when n equals 1, right? So when n equals 1, the summation is going to be summation I goes from 1 to 1, right, of I. So which means that you have only one term, which is 1. So it's going to start with 1, right? But if you use the right hand side, which is a formula, let's look at that when n equals 1. So it's going to be 1 times 1 plus 1 over 2, right? This formula from the right hand side also gives you, let's say, 2 over 2, which is 1. So it actually matches the left hand side, right? So base case is checked out, right? Then second step is called induction hypothesis. We're going to assume that when n equals k, the formula is valid. So this is called induction hypothesis. Hypothesis, right? So this is when n equals k, right? So we don't have to verify anything. This is just an assumption. We assume that when n equals k, this formula works out. So which means that we can assume that summation I goes from 1 to k of I is equal to k times k plus 1 over 2, right? So we can assume that that's as a valid formula, right? Then next step is showing that with this assumption, n equals k, this formula, k plus 1, this formula is also valid. So third step, right? Let's look at the summation. I goes from 1 to k plus 1 of I, right? So since we'd like to use the induction hypotheses, I'm going to split this summation into two parts. First one, I'm going to just sum this up all the way up to just the kth term. So from 1 to k of I, right? Then you have one more term, so you just have to write that as k plus 1. So last term is k plus 1, right? But the good thing is we have a formula for this first term from the induction hypothesis. We can write it as k times quantity k plus 1 over 2, right? And also we can see that here k plus 1 is same thing as, I'm going to take the common denominator, so it's the same thing as 2 times k plus 1 over 2, right? Combine those guys together, so you have a common denominator, which is 2, and there's a common factor k plus 1 and a k plus 1 here, so I'm going to write k plus 1, right? Then you have k plus 2. I'm going to write k plus 2 as k plus 1 plus 1 so that it fits the form, so k plus 1 plus 1, right? So you can see that this is exactly the formula. If n equals k plus 1, you have a k plus 1 here, and you have a k plus 1 plus 1, k plus 1 plus 1 all over 2, all over 2. So this is called the induction step. Induction step, right? So this is when n equals k plus 1, right? All right, so since we checked the base step and the induction hypothesis and induction step, so these three lines will allow us to conclude that for all natural number n, the formula is valid. So summation I goes from 1 to n of I is equal to n times quantity n plus 1 all over 2, right? That's it. Then we can probably say this comes from using 1, 2, and 3. 1, 2, and 3. right? Right, so this is called the proof by mathematical induction, right? I hope that this was clear.